To start things off here, let's take a really quick review of the normal distribution that we learned from the previous chapter. The normal distribution represents one specific overall shape of a continuous distribution. It is that of a bell-shaped curve, and it is symmetric about the mean, mode, and median, which are in the center. The empirical rule applies. Thus, we can state that the area between minus and plus 1 standard deviation of the mean will correspond to 68.26%. We can take a normal distribution and convert it to a standard normal distribution by converting an x value from the original normal distribution to a z value. And once we have that z value, we can then determine the exact areas corresponding to each z-score and compute the probabilities that we're looking for. To start with an x value to go to a z value, we determine the difference between the x value and the population mean and divide by standard deviation. If we algebraically rearrange that formula, we can convert a known z into an x value, as indicated here. Alright, let's see if we can figure out what exactly we mean by the sampling distribution. Notice that the full name here is sampling distribution of the sample mean. So always when we talk about sampling distributions, it will be of one characteristic from that sample. In this case, we'll be looking at the sample mean. A little later on in this chapter, we'll also look at the sample proportion. So, definition of a sampling distribution of a sample mean is the set of the sample means of every possible combination of subsets of a given size from the population. And to illustrate this principle, let's look at a really simple population and correspondingly simple sample. So let's say that we have a population that looks like this. And our population contains 3 elements. The letters A, B, and C are the names that will give those elements. The capital N, population count, is equal to 3, and each element has one variable or x value, and that contains a number. We'll just think of this as an abstract number here. The element A has a value of 20, the element B has a value of 30, and C 100. So in summary so far, our population consists of 3 elements, and each element has a corresponding value. So let's take a sampling distribution of size 2 from this population. So whenever we talk about sampling distributions, they always will relate to one exact sample size. So here our population is size 3, so the only sample size that would make sense to illustrate this would be sample size 2. And let's look over here. So if we were to go back a couple chapters, in how many ways can a combination of 2 be selected from 3 elements? The answer to that is 3 different ways. That sample might randomly select elements A and B, it might randomly select elements A and C, or finally the last possible sample of size 2 with unique elements would be that of elements B and C. And let's look what happens when we take the mean of each of those samples. And before we do that, let's figure out what the actual population mean is. So 3 elements, the total of summation of the x values is 150. Thus, our population mean is 50. Normally, we would not be privy to this knowledge because real world, the whole purpose in taking a sample is to avoid having to measure every element. So with an actual population mean of 50, let's look at what happens to the sample means depending on which specific two elements are randomly selected from that population. Element A and B have values of 20 and 30 respectively, so the sample mean of that would be 50 divided by 2, or 25. The sample consisting of elements A and C would have a sum of 120 and thus a sample mean of 60. And finally, the sample BC would have a corresponding sample mean of 65. So hopefully this is a good illustration of how much sampling error could be present between one individual sample of possible elements and other samples of the same size but of different individual elements. So here we have a range of 40 units with a minimum of 25 and 65. So with a real world type of an experiment, we would typically only take one sample. The sample size would be significantly larger, but still we would only have that one sample to use for our inference. So if this AB happened to be that one sample that we had taken, we would estimate the population mean at 25, but the actual would be 50. So a large sampling error there. And in this sampling distribution, at the lower left of the screen, we have the sampling distribution listed here: sample mean of element AB, sample mean of element AC, sample mean of element BC. And again, because there are exactly 3 possible combinations of 2 elements selected from 3 elements, that's how we know the elements of how many elements the sampling distribution contains. In any non-trivially sized illustration such as this, any normal size sample, there will be a vast number of individual samples. So we don't think of them individually, we think of these as an abstract group, but the benefit that gives us is that it allows us to use the central limit theorem to use the central limit theorem in combination with the characteristics of a normal distribution to be able to apply all of the normal distribution statistical science that we've learned so far and will learn coming up later in the course, throughout the course. What the central limit theorem says is that as a given sample size increases for any sample, the population of all possible sample means, this is what we just looked at on the previous slide, the sampling distribution, that population of all possible sample means becomes approximately normally distributed no matter what the sampled population's native distribution is. So even if the population is no characteristics are known about it, whether or not it's normal, what the shape of it is, a sufficiently large sample size taken from that unknowingly distributed population will always approximate normality, and thus we can use all of our Z tools on it. All other things being equal, populations that are symmetric will require a smaller sample size to approximate normalcy than would a population that was heavily skewed. So if a given population more or less resembles a a bell shape and doesn't have one long tail and the peak of the curve far to one side, then a smaller sample size would be required. And the magic number for any sample to be considered to have a normally distributed sampling distribution has been found to be size 30. So even if the characteristics of the base population are completely unknown, if I have a sample of 30 or more elements from that population, then that sampling distribution, or every possible sample mean of this size from the population, an abstractly large number, will have the normally distributed characteristic, and thus that allows me to apply the Z techniques to it that we've looked at. And the second part of the central limit theorem says that if we have a population that is known to be normally distributed, that a sample of any sample size from that known normally distributed population will have a normally distributed sampling distribution of its sample mean. So if told that a population is normal, I could take a sample of size 5 from that normal population and would be able to consider that distribution to also approximate normality. Thanks for watching this video. Please check the next video for practice problems.